This video covers communication technologies, specifically focusing on source coding. Here is a block diagram illustrating the key elements of a digital communication system, from the source to the destination, including the source encoder and channel. The content for this video includes definitions related to source coding, types of codes, Shannon-Fano and Huffman coding examples, the Shannon source coding theorem, channel capacity of a Gaussian channel, and the trade-off between channel capacity and bandwidth. Source coding is the conversion of a discrete memoryless source output voltage into a binary sequence, or code word, performed by a source encoder. The main goal is to minimize the average bit rate by reducing redundant information. A code word is a group of bits assigned to a source symbol. The length of a code word is the number of binary digits, denoted by NI. Average code word length is calculated as the sum of the product of probability and code word length for all symbols. Coding efficiency is the ratio of theoretical average code word length, h of x, to practical average code word length, L, multiplied by 100. h of x is the entropy. Practical code word length, L, is always greater than or equal to h of x. Coding redundancy is 100 minus the efficiency, in percent. We have different types of codes. Fixed-length codes have a fixed number of binary digits. Variable-length codes do not. Distinguishable codes mean no two code words are the same. Prefix-free codes mean no code word is a prefix to any other code. Uniquely decodable codes allow the original source symbols to be reconstructed from the code word. Instantaneous codes are uniquely decodable codes where the end of a code word is recognized without examining subsequent symbols, also following the prefix-free property. Optimal codes are instantaneous and have the minimum practical average code length. Crafts inequality gives the necessary and sufficient condition for the existence of instantaneous and uniquely decodable codes. The summation of 2 to the power of negative code word length must be less than or equal to 1. We can apply this to different example codes. Consider the problem. Show that all codes satisfy Craft inequality except code B. This table provides the symbols, probabilities, and different code assignments to analyze the condition. In fixed-length coding, the bit rate increases, requiring more bandwidth. In variable-length coding, different numbers of bits are assigned based on symbol probability, decreasing the bit rate and requiring less bandwidth. The two main techniques are Shannon-Fano coding and Huffman coding. The Shannon-Fano coding algorithm involves arranging probabilities in descending order, dividing them into two sets based on the sum of probabilities, assigning zeros and ones to the sets, and repeating until single probability values are reached. Finally, calculate practical average code length, entropy, efficiency, and redundancy. Problem 1 asks to calculate coding efficiency and redundancy for a discrete memoryless source with 5 symbols and given probabilities. The table shows the symbols, probabilities, the step-by-step process of coding, the resulting code words, and their lengths. The calculation for problem 1 shows the average code word length L is 2.1 bits per symbol, and the entropy, h of x, is 1.945 bits per symbol. This results in a coding efficiency of 92.4% and a redundancy of 7.6%. Problem 2 involves a discrete memoryless source with 7 symbols and their corresponding probabilities. The task is to calculate the coding efficiency and redundancy. The table provides the data and the steps for Shannon-Fano coding. This slide provides the formulas for calculating coding efficiency, average code word length, and entropy. Note that the entropy h of x is calculated to be 1.945 bits per symbol, and the average code length L is 2.1 bits per symbol. Calculating efficiency yields a result in percent, and redundancy is 100 minus efficiency. Now let's examine the Huffman coding algorithm, which provides an optimal code. Step 1. Arrange all probabilities in descending order. Step 2. Add the last 2 probabilities and rearrange them in descending order. Step 3. Continue this process until only 2 probability values remain. Step 4. Start assigning binary digits from the last 2 probabilities, assigning 0 to the upper and 1 to the lower probability. Continue this backward process to the first stage to find the code word length Ni. Step 5. Calculate the practical average code length, entropy, coding efficiency, and redundancy. For problem 1, using Huffman coding with the given source symbols and probabilities, the average code word length L is 2.2 bits per symbol, and the entropy, h of x, is 1.77 bits per symbol. The resulting coding efficiency is 80.4%, and redundancy is 19.6%. Problem 2 asks to calculate the coding efficiency and redundancy for a discrete memoryless source with 7 symbols and given probabilities using Huffman coding. The table illustrates the initial symbols and probabilities for problem 2, along with several steps of the reduction process to demonstrate Huffman coding. We see the resulting code lengths for some symbols. The final step is to assign the binary digits and complete the process. After completing the Huffman coding steps for problem 2, we can calculate the average code word length L and the entropy h of x. Using these values, the coding efficiency and redundancy can be determined. Shannon's source coding theorem states that the average code word length L is bounded below by the entropy h of x. The diagram illustrates a discrete memoryless source feeding into a source encoder to produce a binary sequence. Case 1. We start the proof by considering the probability of a code word being represented by a code length. We can use the negative log of the probability, pi, as an ideal code length, li, for each symbol, which will be the minimum average code length. We multiply the ideal length, li, by its probability, pi, and sum it over all symbols. This summation is equal to the entropy, h of x. Therefore, the average code length L must be greater than or equal to the entropy, h of x. Since the code word length Ni must be an integer, it is always greater than or equal to the ideal code length, Li. Summing pi multiplied by Ni over all symbols results in the average code word length, L. This proves the lower bound. L is greater than or equal to h of x. Case 2 proves the upper bound. We start with the Kraft inequality condition that the sum of 2 to the negative code word length must be less than or equal to 1. We compare this to the summation involving the ideal length L and find that L is less than h of x plus 1. Combining the results from case 1 and case 2, we see that the average code word length L is bounded between h of x and h of x plus 1. This concludes the proof of the upper bound of the Shannon source coding theorem. These are the references used for the content presented in this video.